This video refers to a worksheet we refer to as the Candy Crate worksheet. And I'm going to get rid of this for a second just to show you how we made that. We're going to do a force diagram that hopefully will help you to see how the forces are acting on these things. Of course, we're looking at Newton's second law, and this is what I find to be the most helpful version of Newton's second law, because it talks about the acceleration being proportional to the net force on the object. So we have a student looking at a crate of candy, admiring it, and then giving it a little tug to see how heavy it is, and then dragging it off toward their room. So first of all, it is not moving, it's not accelerating. So that's the question you really want to ask yourself on every one of these. Is the object accelerating? And the answer is no. So if the object is not accelerating, the net force on the object must be zero, and the evidence for that is simply what we just said. It is not accelerating. So probably the first question you should ask yourself when dealing with Newton's first law is it accelerating or does it have constant velocity? If it's accelerating, you must have a force or an unbalanced net force, and if it's not accelerating, then your net force must be zero. You must have balanced forces. So let's see what we have here. We'll make a little dot, and this will be the actual box itself, and then we will draw the force of gravity down, and we usually call that Fg. Now this is calling it W, which is weight, which is the same thing as Fg. And there's an N here, and the N is what we refer to as the normal force. And the normal force is the force that comes off of any perpendicular surface. You might be standing on a hill or sitting on a desk. It's called the normal force. So in this case, the normal force and the force of gravity are exactly the same in opposite directions. And so I'll put two little tick marks there to show you that they're exactly the same in opposite directions. So if we add up the total forces, they're going in opposite direction, so they cancel out. So the net force is zero, and the acceleration is zero. It doesn't mean the force is zero, it just means the total forces, when you add them up, directionally speaking, there's zero net force on this object. Okay, so then he gives it a slight pull. He's thinking, okay, I wonder how heavy this thing is. And it turns out, when he gives it the little tug, that this little tug is not going to be enough to actually move it. So he does give it a tug, and we're going to call it the force of the pull, which they have as P here. It doesn't move, not enough to move it, so we know that the force of friction must have stopped it. And since it didn't accelerate, the force of friction is going to be the same in the opposite direction. So this is saying that the force of friction is going to be equal to the pull, and the net force in the crate must be zero, because remember, if the acceleration is zero, the net force must be zero, and the thing is not accelerating. It is in constant velocity. So in the next one, he decides to go for it, and now he's going to increase it so that it's greater than friction. So this pull here is greater than friction, and you know this is what we call budging the box. So this one is greater than the friction, and the box budges, and it begins to accelerate forward. So now we are accelerating and to the right, and we do have a net force. Acceleration is not equal to zero, so it's going to the right, and we do have a net force that's not zero. So the net force is going to be defined as the force of the pull minus the force of friction. So whatever the difference is, that's what we get. So we don't have acceleration of zero, we have acceleration to the right. So the net force in the crate is now greater than zero, and the net force acts to the right. The last situation is confusing to some people because it's moving, but the forces are balanced. What the heck is going on there? Well, it's not accelerating, it's going at constant velocity. So constant velocity by definition means that there is no acceleration. And if there's no acceleration, your net force must be zero even though it's moving. So how much is the friction and the pull here? Well, by this mathematical definition, the friction must be matched to the pull. And if we do this, then we will keep it going at an exact constant rate, and that's our constant velocity. Our acceleration is still